Okay, we're back and ready to talk about our problem here. Let's see, number one, you should have gotten, if you calculate it all the way out, an answer of 24. All right, here's good cheering things going on. What's that, Ben?
21.
You got
I
21.
think it's just a math there.
Plus
Could
three.
be, could be. Here are the calculations that I did to get that portion. Right there. Oops, I'm going to pull that up here. We'll talk about just that part for now. Okay. The definite integral of 3 times f prime of x plus 4, we can break this apart and do it term by term. So 3 times f of x is going to be 3 times the integral of f prime, and then plus 4 can be just plus the integral of 4 dx. 2 pieces we break apart. When I integrate f prime, we're going to get f, evaluated from 0 to 1.5. When I integrate 4 dx, I get 4x, evaluated from 0 to 1.5. Subbing in upper minus lower, I get f of 1.5 minus f of 0. And over here I get 4 times 1.5 minus 0. Looking at the table of values, and this may be where some of you picked out the wrong numbers perhaps, f of 1.5 was given as -1. F of 0 was given as -7. This gives me 6 times 3 is 18. 18 plus 6 gives me 24. Where'd you make a boo-boo, Mr. Ben? I'm curious.
I just did it wrong.
Okay, fair enough. Do you see how I can break it apart and do term by term though? Yeah. Okay. Then we got looking at, find the equation of the tangent line, part B. Okay. So we can get from our table of values that the function value of 1 is -4, function value, derivative of 1 is 5. So point slope form, we got our tangent line. I did go ahead and simplify because I saw where I was going to use it in the next step, but I boxed that in saying here is my answer. And even if you did get this and then went on to simplify it incorrectly, they more than likely would say this point is earned, they use the phrase they banked that one, but as a bank, this is the bank, you can't take it away. Now, it says use this tangent line as an approximation for the function value of 1.2, which is basically summing 1.2 in the tangent line. We get -3. And then is this an will this approximation be less than f of 1.2, or I forget how they phrased it, did they say less than or greater, or just will it be less than?
Less than or greater than.
Okay, less than or greater than. That's going to be determined by the, mainly the concavity. I used increasing, but concavity is the main argument. I'm finding the line tangent at 1, and let's see, there was a point 1, -4. Okay? I had a positive slope, so I got a slope of 5, so it's doing something pretty steep. There's my tangent line. The fact that my curve is concave up for all x says that my curve is doing something. I'll exaggerate it like that. There's my concave up. Thus, here at 1.2, I need a different color. At 1.2, the value of the tangent line is indeed less than the value of the function because of that concave up. My curve will all lie above that tangent line. Part C asked for, is there a value of R such that on that interval 0 to 0.5, that this guy will yield some value of R? And basically, it's just subbing in and cranking it out. I forget how the question was phrased. I'll go ahead and uncover everything.
Find positive row of the number R having the property that there must exist a value C with
Okay.
between 0.5.
Oh, okay, yeah, it says on the interval, and the second derivative of C is R. Okie dokie. Well, the second derivative at any C on this interval, this is mean value theorem. The derivative of some function, if we meet the criteria of mean value theorem, and by what they told us in the prompt, we know it's continuous and differentiable. I know f prime is differentiable because they told me the second derivative is always greater than 0. That means it must exist. It's some positive number. Therefore, the second derivative exists. Therefore, I know I'm continuous and differentiable. And therefore, I know mean value theorem applies. So the second derivative of some C on this interval is going to be, in this case, f prime of b minus f prime of a all over b minus a. This, by using their table of values, cranks out to be 6. So there is a value of R such that this will be true. In part D, let G be this piecewise defined function. The graph of G passes through all the points. Is it possible that f and g are indeed the same function? Well, it's tempting. Very tempting. If they have all the same y coordinates, well, hey, that makes it sound pretty good. If they've got all that stuff, you're fine. But what you got to look at in this thing they gave us is where they broke it up at. All right. If this matches all the points for x is less than 0, and this matches all the points for x greater than 0, what's going on at 0? You got to ask yourself. That's almost the biggest clue you can think of. What's going on at 0? Well, at 0, they both have the same y coordinate, -7. Was that the y coordinate in the table? Yeah, okay, that's cool. And they told us that was going to be the case. Now, so what you got to think about is this going to match up with slope and concavity. You could take the derivative of each one of these and look and see, okay, this is going to be 4x minus 1. That's 4x plus 1. If I sub in our different values for all my negatives, for 4x minus 1, will this give me -7? Well, this will give me -5. Well, that will give me -3, and so on. You can check that. If some of those don't pan out, not the same function. You can take this 4x plus 1. Sub in a half, you should get 3. Sub in 1, you should get 5. Sub in 1.5, you should get 7. I didn't even check that to see if it happens or not. If it doesn't, they're not the same function. What I looked at was the concavity. I found the derivative, and the derivative of the top function is going to be the slopes for all x is less than 0. The derivative of the bottom function is the slopes for all x bigger than 0. And I looked at that guy coming in from left and right. Because the function approaches the same value from left and right, but are the slopes the same from left and right? So I looked at the limit from the left of g prime, and that gave me -1. I looked at the limit from the right of g prime, and that gave me +1. The slopes are different, therefore the second derivative is not continuous. That was my argument. You could have argued it different ways. Scoring guide did, well, they accepted both. So here's our scoring guide for this problem. There we go.
That's very vague.
What's that?
Answers no with reference to G prime and G.
Well, yeah, once again, this isn't how they give us this and say go score them. This is just a very, very, very cut and dried, something they'll email the teachers to have a reference to. But part A was a 2-pointer. If you got the antiderivative, if you integrated this piece and got these two, then you earned the first point. And then if you subbed in correctly and got your either this or 24, you got the second point. Part B, you got 1 point for the tangent line. You got 1 point for calculating the correct y coordinate of -3. And then you got a third point for a good reason. All right. right, part C, you got 1 point for just referencing the mean value theorem, and 1 point for finding this value of R. And D, okay, answers of no with reference to G or G prime, or G prime or G double prime. Okay, so you had to say it was no, and then you had to give some sort of justification, and then your justification had to be right. You may have made an invalid argument, but if you incorporated G prime and G double prime in there, you might have gotten that first point. And if your valid argument wasn't good and solid valid, you might not have gotten the second point. So any part of that got you flabbergasted, or are we good? Good? Okay.
Can we look at the statistics for it?
Pardon me?
The like.
This
average
statistics, 02, question 6, let's see if we can find them. I think it went all the way back to 02 when we were looking at it a moment ago. Nope, it doesn't go that far back. Sorry.
We can just send it.
All right, tell you what, let's do. I want to create a couple of the multiple choice ones we got. We'll just work through those together. And then there's one other open response that does ask us to do a midpoint Riemann sum. We'll jump ahead, do that, and we'll do that same problem as a trapezoidal. That way we can see two different looks. So let's bounce over to well, I'll tell you what. Let's go turn the page. 1998. Oh, we haven't even done this problem. Cool. Well, I think it's the one of the very first, but we did the 90. No, we didn't. We did 97, and then we did 99. We skipped 98. Good enough. All right.
I was like 4 for this test.
All right. Let's look at this guy.
Actually, I was 13. Okay, yeah, sorry.
Let's put it up soon.
So this is the 98 exam.
Shoot. I'm thinking the wrong page.
98 exam, question 3. Let's just kind of go through it together, get it in our heads here real quick. Graph of velocity in feet per second is given here. Car traveling on a straight road, so rectilinear motion along a line. From 0 to 50 is shown above. A table of values, the 5-second intervals is given here. All right. We could have estimated the y coordinates in the graph, but they wanted us to all be able to calculate the same thing, so they give us the y coordinates. All right. During what intervals of time t is the acceleration of the car positive? All right. That's velocity. If that's velocity, what will I know about positive? No, where does it say? Yeah, positive acceleration. What has to be true? Say again, please.
It has to be increasing on velocity on V of t.
Right. V of t has to be increasing because acceleration is derivative velocity. So derivative is slope, and if my curve is increasing, my slope is positive. So I gotta look and say, where is my graph increasing? And let's see, how would we put that answer? During what values or intervals of time is the acceleration of the car positive? So we can say acceleration is positive on the intervals. What? I heard somebody saying something.
0 to 35.
0 to 35. I agree.
45.
And what again did you say?
45 to 50.
45 to 50. Okay. Interval 0 to 35 and 45 to 50. From 0 to 35, indeed, velocity is increasing. Therefore, derivative is going to be positive, and derivative velocity is acceleration. 45 to 50, velocity is increasing, acceleration is positive. All right. So I've got my intervals. I need to give a reason, because on these intervals, velocity is increasing, therefore acceleration will be positive. There's my reason. That'll work. Find the average acceleration of the car in feet per second squared over the interval 0 to 50. I've got two options here what I can do. I'm either going to do average value of a function, or I'm going to do mean value theorem. And they're very, very closely related, as we've seen. Which one do you think I'll have to do? Mean value theorem, because that involves taking the derivative, right? And if I want to find the average acceleration, all I've got is velocity stuff. I'll have to take the derivative to get acceleration. If I had the acceleration function, I could do the average value of the function, but I don't have that. Yeah. So average acceleration on the interval 0 to 50, all right? Will be calculated how? I say a little louder, please.
72 minus 0, 50 minus 0.
Okay, I'll slow that down just a bit. It is going to be the velocity at 50 minus the velocity at 0, all over 50 minus 0. Again here, they tell us almost essentially how to do this right here. Feet per second squared. The units talk to me. This numerator is going to be measured in feet per second, and the denominator is going to be in second. That's feet per second squared. So, sure enough, velocity at 50 from our table of values is 72. Velocity at 0 is 0 over 50. Heck, we got it. 72 over 50, I'm not going to simplify that. 36 over 25, I don't want to go there. And I don't need to put units in it. Heck, they gave me units in the prompt. So 72 fiftieths. Find one approximation for the acceleration of the car at t equals 40. Show computations that lead to your answer. All right. Acceleration of the car at 40. So the acceleration at 40 is going to be approximated by, we have options.
35. No.
What's that, Lee?
Never mind. I don't know what I was saying.
Same thing we just did? Yeah. The acceleration is going to be derivative of velocity. And if I want to approximate the acceleration of 40, well, I don't have a function to take the derivative of, so I can find the slope of the secant line. Mean value theorem. And I think you said it, Lee. You said 35, 45? Yeah. I can go, if I want to find the acceleration of 40, I can find the slope from 35 to 45. That would work. So it's going to be the velocity at 45, which is going to be 60, minus the velocity at 35, which is 81, over 45 minus 35. And I can leave it right there. What you couldn't leave it as is v of 45, whoops. You couldn't leave it as v of 45 minus v of 35. Right here in the numerator. You do actually have to substitute those values in. Show computations that are used to arrive at your answer. We've got it. Good enough. Now it says show one approximation. This is one. As Megan pointed out, heck, I could go from 25 to 50. That could be an approximation for 40. I think what we've done is the best one, though. Okay? And that's the one I want you to do. All right, here we go. Part D. I want to see us about doing this guy. I want to approximate this integral 0 to 50 of v of t dt with a Riemann sum. A midpoint Riemann sum. Using the midpoints of 5 subintervals of equal length. Alright. So you guys take a few moments and jot down what you think the midpoint Riemann sum is going to be. We'll talk about that. And I'm going to actually go ahead and we'll do the arithmetic and get our approximation. We'll come back with a trapezoidal. see see if they're gonna be pretty darn close. And they should be. Because both midpoints and trapezoidals are good approximations.
Alright, Miss Bill.
I shall see the photos.
I do laughing, but every time I see that, I think I'm Miss Tiller goes, I was the person who moved out late in high school. Then it makes me mad.
Okay.
Me and Lee have the same feelings about Miss Tiller. I'll say what those feelings were.
Okay. Okay, so we're here. How have we done with our midpoint Riemann sum? I've got mine up on the board.
Yeah.
So it's gonna be adding up a bunch of rectangles. The height of the rectangle is gonna be at the x value on the midpoint of the interval. It's gonna be the function's value there, times the width of that interval. They wanted 5 subintervals of equal width, I think, or just 5 subintervals of equal length. So we had to go 0 to 10, midpoint being 5, 10 to 20, midpoint being 15, to 30 to 40 to 50, and so on. So we pull out the right function values, yes, Brenda,
I didn't say that.
sorry.
That's alright. I put, in the
calculate the area under the curve from P equals 0 to P equals 50, so with that.
Yeah, it does do that. I don't think that's gonna be what they're wanting though. They're gonna be wanting in the context of this problem in terms of the units of this problem and the car traveling down the road stuff. Yeah, I don't know that just saying area under the curve is gonna score it for this guy.
Are they particular about the approximately equal to or the
Yep.
equal to?
Yep,
So you
yep,
have
this
to-
isn't, this is a Riemann sum is an approximation, especially when it says approximate right there. So I did approximate, now this approximation is equal to that number.
Well, like if we just put slash, they'd be that picky.
I think I remembered in one of the readings they were that picky,
Right.
because it is not equal to, it's an approximation for. All right, so I use the phrasing of displacement of the car, or the difference in position at 50 and position at 0. Because of course we know integral velocity is position, and by fundamental theorem calculus it'll be a position at 50 minus position at 0, upper minus lower, the difference in their positions. And because this curve did change increasing to decreasing back to increasing, well, no, that's not true. Did this car change direction? No, my velocities were all positive, weren't they? So my car was always traveling essentially right down the road. Sometimes I was going faster and sometimes I was slowing down. Maybe he was booking it, and he either came up on a curve or he saw a cop. He started slowing down, but he's still going forward. And after he passed the cop, he took off back faster again, maybe.
I'd say he saw a cop because it's on a straight road.
Maybe he passed and saw a deer and he wanted to slow down looking at the deer. Maybe that's what it was.
Or he thought the deer was gonna jump out in front of his car.
What was that?
Or he thought the deer was gonna jump out in
Thought
front
the
of
deer was
his
gonna
car.
jump in front of his car. Could be. Could be. Yes, ma'am.
Okay, so like in my answer, I put
He was
feet
only going
up
55
by the
miles an
number.
hour.
Excuse me?
Like I put my units for 2,530 feet. Did I need to include feet in my my meaning, like explanation?
Well, I would like to see that, just to be safe. It says using correct units explain the meaning of the integral.
Okay.
So it's kind of implying put the units in the explanation.
Okay.
If you had them there and didn't reference it down here, I think you'd be okay. Because if you did 25, 30 feet,
Yeah.
and this is the displacement of the car over the time interval,
Yeah.
you've got it there. But again, I'm going to be cautious.
Yeah.
All right, so let's see this guy. We've got 25, 30 feet with a midpoint Riemann sum. Let's do a trapezoidal approximation, and let's just say just do 5 trapezoids. We could do, I think 10. Let's just do 5. That way we'll have some calculations, okay? Let's do a 5 trapezoidal approximation and see if we get something close to our same number. my arithmetic right?
I got 2640.
Yeah.
Me too.
2665?
2640.
Would it be easier on your arithmetic to pull out the 1/2
Probably.
and then just add 27? That's probably should be fine.
I must have made a little boo-boo in here somewhere. So what was the final tally?
2640.
Okay. I guess that wasn't right? No, obviously not. Well, it could have been. I may have just done the division wrong.
I think you, between your, like, all of your individual terms and then the one where you have like 10 times 20 over
Boom,
2.
boom.
No, between that one and, never mind, your 10 times all that jazz at the bottom, those numbers add up to 533 over 2, which is 2665, but I think your numbers are wrong.
You think these are wrong?
Yes.
Could be.
Yeah.
Okay. 20, 75, whatever that matter.
It's
120.
133 instead of 138.
That's
Yeah,
it.
133.
I just caught it, same as you, yeah. Okie dokie. And that's why we don't simplify.
Would it be easier if you were to just take the 10 and 1/2 out?
Sure, it would have, yeah. I just, you know,
Probably
6 of
pretty
one, half dozen
easy
the other.
just to use the
Either way.
calculator.
That's what we'll use a calculator for. But yeah,
Are you wanting the video
AP,
camera?
the true test itself, I would have stopped her right there. Boom, I'm done. Not gonna mess with it, not gonna add 2 numbers or anything. Yes, sir.
You want the camera to get that, because it's...
Oh, it's not getting all the way?
It's cutting off.
Well, shoot. Thank you, Lee. Yep, a little bit off there. So we've cut off the last little bit, unfortunately. There we go. All right. We had a couple of calculations when we did the midpoint Riemann sum. We had 2,530 was the final answer. When we went back and did as a trapezoid with 5 trapezoids, we got 2,640 as the final answer. I think those 2 numbers were probably cut off in the video earlier. All right. That's got that. Let's crank through some multiple choice together. We got 15 minutes left. Let's see what we can do. Okay. Let's see. The 1 through 3 are no calculator, and 4 through 9 are going to be with calculator. So let's just do these together. Let me get my camera back centered on my pull down screen. There we go. And I got to remember, I'll tell you what I need to do. Let me flip this little lens thingy around. Maybe I can see when I'm not in the picture. All right. Ooh, guess I'm gonna zoom out of that. All right. All right, question 1. The function f is continuous on the closed interval 2 to 8 and has values given in the table above. Using these subresults, okay, trapezoid approximation. Okay. So I have to simplify a little bit here. Hopefully this arithmetic will work out. I think I might be cutting a little bit off my screen yet again. I'm going to condense it over here. We got the 10 plus 30 as my two function heights divided by 2 times the width of 3. 30 plus 40 divided by 2, the average of the heights times the width of 2. The average of 40 and 20 times the width of 1. And that's going to give me 40 divided by 2 is 20 times 3 is 60 plus 70 plus another 30. And I'm going to get 160. So I'm going to say in C. What do we think?
I agree.
All right. Number 2 here. Oh, we saw something like this yesterday, I think. Table above gives values of f, f prime, g, and g prime. If h of x is f of g of x, looks like a typo here. There should be another closed parentheses after that g of x. Then h prime of 1 is what? Okay, this guy is going to involve chain rule derivative, and then it's a matter of just substituting our numbers in. Taking the derivative of h of x, we're going to get the derivative of the whole thing. So f prime of g of x times the derivative of what's inside g prime of x. Substituting now, h prime of 1 is going to be f prime of g of 1 times g prime of 1. And from our table, let's see. G of 1 is given to us as -1. And g prime of 1 is given as 2. F prime of that -1 is going to be 5. And that 5 times that 2 gives me a final answer of 10. I vote D. Got lots of nice nods around the room. Sounds good. Sounds good. Whoa. I'm not going to get this whole thing on the page. Okay. All right. Let me read this for the guys on the video because you'll never be able to see this, I don't think. For all x in the closed interval 2 to 5, and each of our tables goes from x equals 2 to 5, the function f has a positive first derivative and negative second derivative. Which of the following could be a table of values for f? Okay. If I've got a positive first derivative, then I know my function's always doing what? Increasing. I should be able to look at my y coordinates. If they're not always increasing, vote them off the island. Choice A here, always increasing. He's a keeper so far. Choice B, increasing, keeper. Choice C, nope, it's going down. Vote him off. Choice D, going down. Decreasing values, vote him off. Choice E, decreasing values, vote that off. So it's between A and B. Narrow it down to 2. If we get stupid all of a sudden, we can guess. But we're not going to get stupid. Alright? It says the second derivative is negative. So how can I test that? Lee's doing this thing. Alright?
Concave down.
Concavity. How are you going to tell concavity from those points?
You could graph them.
We could graph them. Okay, it's multiple choice. They're not going to know how we came to the conclusion. It better be pretty convincing. Let's see what it looks like. I'm gonna pull the screen up, so I'm making sure I gotta have a little glare, I know on the video, but let's go with it for this one. Ooh, lost my points though. Let's see. A, you guys help me with these values. 2, oh, I might have to go pretty big, aren't I? See, that's part of the problem with this. I'm going all the way from 7 up to 16. That might be a little iffy, because if you don't get your scale pretty ding dang good, you might not know for sure what it's doing. We can try this. Alright, I'll graph A here, and I'm going to go, was it 2 to 3 to 4 to 5? So 1, 2, 3, 4, 5, and well, might as well go 1 to 16. Alright, there's 16. At 5, I'm at 16. At 2, I'm at 7. 1, 2, 3, 4, 5, 6, 7. At 3, I'm at 9. Alright. At 4, I'm at 12. Boy, it looks concave up-ish. Well, that's a hand sketch. Okay. I might be able to convince myself that's concave up, therefore my second derivative is positive. Okay, so I'm thinking he's not it. If I base it solely on that and choose B, I might rock and roll on with the test and I might be fine. We might want to test D if we're going to go with this same logic. Let's plot some points. We got 2, 7, so still right there. We've got 3, 11, so that puts me here. We've got 4, 14 there, and we've got 5, 16 here. If I've got a decent sketch,